graph that they kind of looked like trees when we were done. And it turns out that's true. If you were to do a depth first search, you start at a node and you're following everything, since you are not ever going back to a visited node, you end up with something that when you're done, if you marked all the edges that you went along, you would have a tree when you're done, because you wouldn't have any sibling connections. And it would start, the root would be the node you started at, but it would just be a tree. So a spanning tree is a tree of an undirected connected graph without cycles. It's a tree, or that is what a tree is, sorry. A tree is an undirected connected graph, right? It's just a graph with no cycles. A spanning tree, which we'll find out in a second, is a tree that you could put on top of a graph that covers all of the nodes. But let's notice a couple things about undirected graphs. Number one, a connected undirected graph with n vertices must have at least n-1 edges. All right, so there's a couple things to note here. It's a connected graph, all right? So, here's 5 nodes. Do any of you think you could draw edges on here, draw 3 or fewer edges, and make that a connected graph? 3 or fewer? Yep. No. I bet no matter how hard you think about it, you will not be able to. No. I mean, maybe it's tantalizing to try and think of it, but there's no way. I need an edge here. I need an edge here. I need one here, here, and here. There's 4. I'm going to need at least 4 edges. I can't get away with less than that. Right? So that's what this is saying. Connected undirected graph with n vertices. It has to have at least n-1 edges to be connected. All right? Hopefully you're convinced. A connected undirected graph with n edges, or n vertices, sorry, and exactly n-1 edges cannot contain a cycle. Actually, I was wrong when I said this. 4 would be 1, 2, 3, 4. Okay. So, if I have n edges, or n nodes, 5, and 4 edges, can one of you draw this so that it is connected and has a cycle with 4 edges? No. I mean, move this to here and I have a cycle, right? But I'm not connected to this node anymore. So if I try and move any of these edges to make a cycle, I break something. I lose one of the nodes. So it is not possible for me to have a connected undirected graph without cycles, acyclic, if I have if I have that, then it has exactly n-1 edges. Okay. Can I add another edge in here without creating a cycle? We just said we can't remove it.
Yes.
No. Where would I put? Let's just label these. A, B, C, D, E. Where would I put an edge, add another edge without making a cycle? Any cycle. Can't think of anything, right? No, you can't. So if I add another edge, I'm going to have a cycle. So n nodes, n-1 edges, no cycles. n-2 edges, not connected. N edges, cycles. And so that's the last thing it says. A connected under graph with n vertices more than n-1 edges contains at least 1 cycle. This math is going to help us, actually. So I have again, just to reiterate, if it's connected, it has to have at least n minus 1 edges. If it is acyclic, it must have exactly n minus 1 edges. If it has n or more edges, then it has cycles. All right, so here is this graph that we've looked at many times. Just ignore the dashed lines for a second. Pretend that they're solid lines. So this is a graph we've been working with several times today. A spanning tree would be, well, first of all, remember solid lines. Are there cycles in this graph?
Yeah.
No. Solid lines, dashed lines are solid. Right? So,
Yeah.
right? So yeah, there's plenty of cycles. We got this one, we got this one, we got this one. I mean, there's plenty of cycles in this tree, okay? So how many edges?
11.
Yeah, I count 11. Yeah, and how many nodes?
9.
I count 9 nodes.
Yeah.
Okay, so is 11 greater than 9?
Yeah.
Mhm.
So our rule that we saw before said that if I want to have a connected acyclic graph, I have to have n minus 1 edges, so I have to have 8 edges, right? So a spanning tree would be a connected acyclic graph over here. So I can create a spanning tree by making sure that I just have 8 edges. So how would I get from these 11 edges to 8 edges?
Prim's algorithm.
Well, Prim's algorithm, I don't think so. This one does it. Prim's algorithm has weights in it. This one, this algorithm would do it. This is a DFS. And what we do is every edge that we visit, or every edge we use to visit a node, we mark that edge as a part of the spanning tree. So, and there's another way that we could do this. What we don't want to do, well, basically, we have 11 edges, we need 8. We just need to remove any 3 edges. It doesn't really matter what tree we remove, and we'll end up with a mid-span tree. Or we'll end up with a spanning tree. But yes, we have to make sure we don't disconnect anything. So in order, we can't just randomly pick edges to remove them. We have to only pick edges that aren't going to leave anything disconnected. So that's why we would use a depth first algorithm. So our depth first that start with A goes in this order, alphabetically, conveniently. And so we mark each one as we visit, A to B to C to D to G to E, then back here, then F, then back to H, and then finally to I. But we mark each edge that we use, mark each edge that we follow, and then we're done. Any of the non-marked edges we throw away. And now we're down to 8 edges. And when we have 8 edges, we know we are connected, and we know that we don't have any cycles. So this is one way of creating what's called a spanning tree. Spanning trees are kind of nice because what they do is they give us a kind of a minimal set that says, okay, yeah, I've got all these nodes and all these connections, but a spanning tree kind of tells me the minimum that is necessary to reach everything, just in terms of edges. Now what it doesn't do is if this was a weighted, if this was a weighted tree, so I had weights on these edges, what it doesn't tell me is how do I know I got rid of the most expensive edges? So if we think of these edges as costs, then we might want to find a spanning tree that is minimum cost. This is what we call a minimum spanning tree or a min-span tree. So I think an application for this might be, I generally think of like trucks on a map, right? You've got a distribution center, you want to send a bunch of trucks out to hit all your cities. And now there's another problem called traveling salesman's problem, which we'll talk about next week, which is how to get one person to go to all the places with the least cost. But that's not this problem. This problem is, I have as many trucks as I want. And how am I going to get them all out to all these places without, with the fewest miles? And so I can make a minimum spanning tree starting with my current location and figure out the min path. So here, if I was to do my normal algorithm where I did A, B, C, D, G, E, F, I, or H, and then I, then remember the nodes I throw out, the weights I throw out are 3, 9, and 4, so 16. I think we're going to find here that that's actually not the cheapest. There might be a way, for example, I might be able to get rid of this 8, because look, I could get to G this way, and my total cost is 6, as opposed from A to G of a 6 versus 6 plus 9 plus 8. So that's a lot more expensive to get there. So the next algorithm we're going to look at is Prim's algorithm, which is how we can find a minimum spanning tree. Okay, so this algorithm, I'll describe it in pseudocode, and we'll step through an example in the diagrams. So it is not a recursive algorithm. We start with a vertex, our starting point, and we mark V as visited, and we include it in the minimum spanning tree. Then, while there are unvisited nodes, notice this is not unvisited nodes adjacent to V, this is unvisited nodes. There are nodes that have not been visited yet. So while there are unvisited nodes, find the least cost edge from V, which is my node I'm starting with, to U, from a visited vertex V to some unvisited vertex U. Actually, so the V is not this one anymore. So V is any node that's visited. I have my set of visited nodes. And in U are a set of unvisited. So find the least cost edge from something in my visited set to something in my unvisited set. When I find that, I mark U, the unvisited one, as visited, and then I add that edge, the V to U edge, to my min span tree. Then I go back and top my loop. Are there still unvisited nodes? Yes. Okay, great. So here's all my visited ones. For my unvisited ones, what's the smallest path forward? Okay, now let's look through this as a diagram. I am going to start with, oh, by the way, an adjacency matrix is perfect for this. I'm starting with A, and in my adjacency matrix, I have a row that tells me everything that I'm adjacent to and the cost to get there, right? And so I can go down that list and I can say infinite, infinite, infinite. Oh, that one's a 2, that one's a 4, that one's a 6. And the infinites are obviously very expensive. And so the other ones are cheaper. So the least cost, the first time I go down, when I start with A, the least cost is the one to I. So these costs, we're just going to assume they're all correct in these charts, so I'm not going to keep flipping, or in these graphs, I'm not going to keep flipping back them. So the least cost is to I. Now, step 2, how many nodes are in my visited set? 2, A and I. Everything else is unvisited. Okay? So now I look at all the paths from A or I to something else, and what's cheapest? Well, this is actually going to be cheapest. There's nothing from I, so no contribution there. But from A to F, the cheapest, and that's 4. So I'm going to take that one. Keep the A, and I add that. So I'm going to add F to the list now. So A, F, and I. And again, from that list, I say, what can I get to next, and what's the cheapest? From A, F, and I, there's only 2 places I can end up. I can go to B with a cost of 6, or I can go to G with a cost of 2. So I'm going to pick G, that's the cheapest one. So I pick G, add that to my list. So these are all in my visited node list. These are not. So now again, I can take 6 to get to B, 8 to get to E, 5 to get to D. I'm going to pick this one. That's the cheapest one. Added that. Now I have this, this, and that. This is the cheapest one. So I add that in. Now I've got these options. This is the cheapest one. So I'll take that. Now I've got these options. Notice that I've got 2 ways to get to B here. But of the edges I can follow, a 7, a 3, an 8, and a 6. This is the cheapest, so I'll take that. Now this edge is gone because this has been visited, so the G to E edge doesn't count anymore because E is now in the visited set. I got there a different way. And now the cheapest one is here, so I hit that one and I'm done. So I do have a spanning tree, starting with A as the root. Actually, I think any node is the root.
Yeah, you can.
Yeah. But I'm starting with A as the root, and this guarantees that it's the min cost spanning tree. Then when I start with A, if I started somewhere else, I don't know if I get the same min cost. I haven't tried that. Do you?
Yeah, this was covered in one of my other classes.
Okay.
And you can start anywhere and you get the same thing.
Okay. So that's Prim's algorithm. So it's actually pretty straightforward when you start thinking through it, right? Or does it just sound easy to me? So obviously there's some work to do if you're actually implementing it, if you're using adjacency matrix or adjacent you've got some kind of administrative work to do to make it work. But the thinking part is pretty straightforward. Okay, so and the min span tree has the uses, like I said, this idea of a distribution or something like that. This is, yeah, okay. Shortest path. This is, we're not going to do shortest path. This is where we're going to stop. But I'll just introduce it. Here's a different graph. This is a directed acyclic node. It's got cycles. This is just a weighted directed graph. Shortest path between 2 vertices in a weighted graph is the smallest edge weight. So the min span tree was actually creating a tree covering all the nodes. Shortest path says, given, I'm going to start with at 0, and I want to find the shortest path to get to 2. Now you might say, oh, that's easy. You go from here to here to here, but that cost is 9. This would be cheaper.
Well, no, that's what, 4? Yeah.
4 plus 1, so that's at a cost of 5. Now, obviously, as a human, you can look at this and you could do a little bit of thinking and figure it out. But imagine if this wasn't just 5 nodes, this was 10,000 nodes and a bazillion edges, then figuring this out becomes harder. So next week, that's kind of what we're going to start with. This is an algorithm to this. There's an algorithm called Dijkstra's shortest path algorithm. What?
That's what you can.
Yeah, that's how you pronounce it, Dijkstra. So Dijkstra's shortest path algorithm, and we'll walk through how we can do this. So that's all the material I wanted to cover today. Like I said, we'll end a little early, but I think that your brains are probably full. Yes? Pretty close
Full,
to
but
it.
also on empty as well. Just
Full and empty. But because there's been a lot of material today, so I want to give you a chance. I don't want to pile on more. Let you kind of process it. So, any questions though, about what we've done so far? No. So it's all super easy,
no, just let it
or your
process.
brains are so full you don't even know how to ask a question. Just let it process.
I'll email you a question if I have one.
Okay. Then we're done for today, and I will see all of you next week. Remember, design questions for the experiments program are due next Wednesday. I will try and actually give responses to the design questions as they come in, so if you turn it in sooner, I might give you responses sooner. Housing is due this Sunday. I hope though that you start on experiments before then. I know that it's hard to have two going at the same time, but experiments is going to take some time. It's scaled down to fit in the time frame, but it still is a tree, and you haven't done trees before. It's still using char stars for strings, and those have columns sometimes, so make sure you give yourself time.
That's an interesting point. So